Chemistry, we're on to our last lesson in the reactions unit, Unit 2, and this is on a concept called limiting reactants. Okay, so I'm going to give you an exercise. How many cakes can you bake? So to bake one cake, you need 1 cup of milk. To bake 10 cakes, you need 10 times that many, or 10 cups of milk. To bake 1 cake, you need 2 cups of sugar. 10 cakes is going to take 20 cups of sugar. 1 cake is going to take 5 cups of flour. 10 cakes is 10 times that, 50 cups of flour. 1 cake is 3 sticks of butter. 10 cakes is 30 sticks of butter. 1 cake is 6 eggs. 10 cakes is 60 eggs. So tell me how many cakes you can bake if I give you the following quantities of ingredients. You get 10 cups of milk, 20 cups of sugar, 50 cups of flour, 30 sticks of butter, and finally you get 6 eggs. Okay? So think about it. How many cakes can you bake with that many ingredients? Okay, so let me give you the answer. The third column can produce only 1 cake because there are only enough eggs for 1 cake. But what about all the other ingredients? Well, you just can't use them. You got to put them back in the cabinet, use them some other time because you only had enough eggs to make 1 cake. So it's the number of eggs that limited how many cakes you could make. And that's the concept of a limiting reactant. The eggs here ran out first. They ran out before the other ingredients, so it limited how many cakes that you could make. So when you're running a chemical reaction, the reactant that runs out first is called the limiting reactant. That limits how far or how much of the products you can make in that reaction. So limiting reactants deal with situations where one of the reactants is consumed, that is, runs out before the other. In a limiting reactant problem, we want to be able to identify the limiting reactant, the reactant that runs out first, the excess reactant, the reactant that is not completely consumed, the amount of excess reactant remaining, and the quantity of products that can be produced. In the following combustion reaction, 2 moles of O2, oxygen gas, react with 1 mole of CH4 gas. So there we've seen this reaction before, but what if there are more or less than 2 moles of O2 for every 1 mole of CH4? What will happen? Well, then either the CH4 will run out first or the O2 will run out first. It just depends on how much of the O2 that you had. Then one of the reactants will run out before the other. The way to perform the excess reactant problem above is to run the reaction twice. Once in which all of the CH4 is completely used up, and then a second time in which all of the O2 is completely used up. So here's our example. We're going to take 6.42 grams of CH4 and 35.2 grams of O2, and they're going to be reacted in a combustion reaction, and we want to be able to determine the limiting reactant, the excess reactant, the amount of excess reactant remaining, the number of moles of CO2 produced, and the number of moles of H2O produced. So there's the problem. So first we convert grams to moles. Always, always when you're dealing with a chemical compound formula or a chemical reaction, it has to be in moles. Chemical reactions do not understand grams. So you have to convert from grams to moles using molar mass. So there you have 6.42 grams of CH4 that we were given. We have the molar mass of CH4. 1 mole equals 16.04 grams. Again, you calculate that using the periodic table. We need grams of CH4 on the bottom of that ratio so that it will cancel with grams of CH4 over on the left. And then you want moles of CH4 to show up in your final answer. And when you do that calculation, you get 0.40 moles of CH4. We'll do the same thing with oxygen, 32.52 grams of oxygen. We have our conversion factor for oxygen, and we need grams of O2 on the bottom, so it cancels with grams of O2 on the top. And then that leaves us with 1.1 moles of O2. Now we're going to run the two reactions. Reaction 1 uses up all 0.4 moles of CH4. Reaction 2 uses up all 1.1 moles of O2. Set two rows of boxes below the reactants to run each reaction. So the top row is going to be where we use all of the CH4. The bottom row is going to be where we use all of the O2. Okay, so that's what we have to work with in terms of moles. 0.4 moles of CH4 is what we've been given, and 1.1 moles of O2 is what we've been given. There's the boxes. There we're setting it up, top and bottom. Reaction 1, the top row uses up all of the CH4, and the bottom row uses up all of the O2. So we're going to go ahead and place the numbers in. So when use all the CH4, well, how much do we have? We have 0.4 moles. So we're going to put that in that box. Now you have to do a little calculation. You need 2 moles of O2 for every 1 mole of CH4. That's what the chemical equation tells us. So what is 2 times 0.4? What amount of O2 would that be? And that would be 0.8 moles of O2. Twice as many moles of O2 as moles of CH4. Now we're going to go down below and we're going to burn all of the O2. We're going to use up all of the O2. And how much O2 do we have to use? That's 1.1 moles of O2. So now, again, we need twice as much O2 as CH4. So if we have 2 to 1 O2 to CH4 and we have 1.1 moles of O2, how many moles of CH4? So what you're going to need to do is divide 1.1 by 2, and you'll get the moles of CH4, and that's 0.55. So if that seemed not quite clear or a little confusing, just notice that all the relationships are 2 to 1. The chemical equation is 2 oxygen for every 1 CH4. The first row is 0.8 oxygen for 0.4 moles of CH4. That's a 2 to 1 relationship. And the bottom row is 1.1 moles of oxygen for every 0.55 moles of CH4. Again, that's a 2 to 1 relationship. So now we have to ask ourselves the question, do we have at least this many moles to work with for each of those 4 boxes? So the phrase at least as many or at least this many means that many or more. Do we have that many or more moles to work with? So let's go around. 0.40. Do we have at least 0.40 moles of CH4? Yes, we have exactly 0.40 moles of CH4. Look up above, that's what we're given. How about 0.80 moles of O2? The answer is yes. Look up above. We have 1.1 moles of O2. So yes, we have at least that much. We have 0.80 moles or more. So yes, we have at least that much. Now let's go down below. 1.1 moles of O2. Yes, we have exactly 1.1 moles of O2, so we have at least that many or more. Now we go over to the box under CH4. Do we have at least 0.55 moles of CH4? What do you think? The answer is no. We only have 0.40 moles of CH4, so we do not have 0.55 moles. We do not have enough CH4 to burn all of the O2 that we were given. So the column with the no in it is the limiting reactant. Okay, and the column with the 2 yeses in it is going to be the excess reactant, and that's the O2. So O2 is the excess reactant. Now let's look at how these reactions are going to take place. If you look at the top row reaction, the one use all CH4, you're going to burn through all the CH4 before you burn through all the oxygen. So yes, you have enough of both of those compounds to make that reaction go to completion where all the CH4 is used up. Okay, if you look down below in the use all O2, you're going to need 0.55 moles of CH4 to burn 1.1 moles of O2. You don't have 0.55 moles of CH4, so the CH4 is going to run out first. Okay, so the reaction that's actually going to work is the one on the top. That you burn all the CH4, 0.40 moles, and you burn 0.8 moles of your O2. So how much O2 are you going to have left over? Well, you started with 1.1. You had to use 0.8 in the top row reaction. So 1.1 minus 0.8 equals 0.3 moles. So the excess is 0.3 moles of O2. That's the amount of your excess reactant you have left over. You can put it away and use it some other time. The row in the green box is the reaction that can run completely. So that's what we just said. We can use all the CH4 without running out of O2. So this reaction will run because there are at least 0.4 moles of CH4 and at least 0.8 moles of O2. So that will run. This reaction will not run because there's not 0.55 moles of CH4, so you're going to run out of CH4 before you've used all of your O2. So the CH4 is like the eggs in the cake example. It's the one that runs out first, and it limits how far this reaction can go. So the row with 2 yes in it is the reaction that will run. This is the reaction in the green box. Now we can compute the number of moles of CO2 and H2O that can be produced from the reaction. So the equation tells us that we will produce the same number of moles of CO2, that's 1 mole, as moles of CH4, that's 1 mole. They both have coefficients of 1. So you're going to end up with the same number of moles of CO2 as you started with moles, or as you combusted moles of CH4. And that's 0.4. So you can go ahead and put a 0.4 there. It's a 1-to-1 relationship. They're even. We will produce the same number of moles of H2O, that's 2 moles, as moles of O2 because they both have coefficients of 2 in front of them. So we can go ahead and put a 0.80 there. We also could have just simply said that we're going to get twice as many moles of water, H2O, as we had moles of CO2. So we would simply take the 0.4 and double it. So that's how you find that out. Now, using molar mass conversions, we can compute the grams of CO2 and H2O if we wish, but we're not going to do that here. Okay, now we're going to deal with the concept of percent yield and theoretical yield and actual yield. So the theoretical yield of products in a chemical reaction is the amount of chemical that the chemical reaction says you should get. In other words, when you do it on a pencil to paper and you do the stoichiometry, it says this is what you should get for your products. The actual yield is how much you actually get in the lab. So actual yield can differ from theoretical yield for several reasons. Human error in measurement, you just measured something wrong. Material lost by remaining in the container, or you spilled a little bit of it, or some of it evaporated out. So it's the real world versus the theoretical world. So the difference between the actual and the theoretical yield is measured by percent yield. So the percent yield is the actual yield, that's what you got in the lab, over the theoretical yield, that's what you figured out on pencil to paper that you should have gotten, times 100%. Okay, so we're going to run through a quick stoichiometry here of what we did earlier, of this equation that we used earlier. So compute the theoretical yield and percent yield for grams of water for the following balanced reaction if 6.5 grams of CH4 is combusted in excess oxygen. The actual yield in the lab is 12.9 grams of H2O. So 12.9 grams of H2O is what you measured when you came out of the lab. It's what you measured in the lab. So if you put in 6.5 grams of CH4 and you combusted it in excess oxygen, how much water should you come up with? Now there's a phrase there that you should get used to hearing, and it's in excess oxygen. Now you know what that means. It means that when you run this reaction, the oxygen is not the reactant that's going to run out first. You have enough oxygen to combust all of the CH4 that you have. So get used to seeing that expression. You'll see it a lot in high-level chemistry problems. So in excess oxygen means oxygen is going to be your excess reactant. It is not going to be your limiting reactant. Okay, so here we go. We're going to start with grams, and you don't have to do the calculation here. I'll do it for you. So you have 6.5 grams of CH4. You use the molar mass of CH4 to get the number of moles, and there's the 0.4 that we got in the earlier problem. Now you have to convert that to moles of H2O. You have 2 moles of H2O for every 1 mole of CH4, so that means you have 0.80 moles of H2O. Again, be sure you're following how these numbers are changing. And now you need to come back out. Now we do need to figure out how many grams of water. So you use the molar mass of H2O. 1 mole equals 18.02 grams. And what does that equal? That equals 14.4 grams. So in theory, 6.5 grams of CH4 should have given you 14.4 grams of O2. But it says that the actual yield in the lab that you measured was only 12.09 grams of H2O. It says that in the problem. So there's the problem rewritten. So the actual yield is 12.09 grams. So the yield H2O from this reaction should be 14.4 grams, calculated below. This is the theoretical yield. So there we go. That's the computation, the calculation I just did for you. So 6.5 times the molar mass of CH4 gives you the moles of CH4. You have 2 moles of H2O for every 1 mole of CH4. And then you use the molar mass of H2O to get back out from moles of H2O to grams of H2O, and you get 14.4. That's what the equation told you should have gotten. So percent yield is computed as follows. What you actually got in the lab, 12.09 grams of H2O, over what the equation said you should have gotten, 14.4. You multiply that by 100% and you get 84%. So this means we actually obtained 84% as much water as the chemical equation predicted. It's almost always true that your actual yield and your theoretical yield will not be the same for exactly the reasons that were mentioned previously. Could be error on your part, it could be evaporation, spillage, some of it just sticks to the container. Now, if you come out with an actual yield that's greater than your theoretical yield, that's really odd. You should never end up with more. That's clearly then a measurement problem. That you made an incorrect measurement somewhere along the way. Okay, we're going to wrap up this lesson in this unit with the 5 basic types of reactions. So there are 5 basic structures for chemical reactions. These are synthesis or combination reactions. 2 or more elements are combined to form a compound. So carbon plus oxygen gives you CO2. Decomposition reactions, a compound is broken into 2 or more elements or compounds. So you saw this one back when we were doing empirical formula. So silver oxide produces silver and oxygen. And notice the oxygen is O2. Oxygen always comes out as a molecule, O2. It does not come out as a single atom. Single replacement reactions, an element takes the place of a cation in an ionic bond. These are seen in activity series reactions, which we'll deal with in more detail at a later time. So the copper and the fluorides are forming an ionic bond. The copper has given up 2 electrons, and each of the fluorides is taken in 1, so they form an ionic bond. So the copper in that compound is actually a 2+ cation. Now the zinc is sitting out there in its natural state. It's electrically neutral. What the zinc does is it gives up 2 electrons to the copper. That means the copper got back the 2 electrons it lost to fluorine, so it's now neutral. So if it's neutral, it no longer has a reason to want to stick to the fluorine because it doesn't have a charge anymore. So it goes off by itself. And the zinc, which lost 2 electrons to the copper, it now has a 2+ charge, so it goes over and sticks to the fluorine. So that's why on the right side you see the copper by itself and the zinc bonded ionically to the fluorine. Now, will this happen? How do you know the zinc is going to pass the electrons to the copper or not? Well, that's when we study activity series, we'll answer that question. Double replacement reactions, the cations of 2 ionic compounds switch ions. So we will see this in precipitation reactions. So there you have potassium iodide, Ki, and lead nitrate, PbNO3, and what happens is the K, the cation, potassium, and the cation lead switch places. So now the K, the potassium, is with nitrate, and the lead, Pb, is with iodate. So the 2 switch places, so that's a double replacement reaction. And finally, the last one we've seen quite a bit, these are combustion reactions. A hydrocarbon, a CH compound, or carbohydrate, CHO compound, are burned in oxygen to produce carbon dioxide and water. So a combustion reaction always looks exactly like this, except the hydrocarbon at the beginning will be different. There's a lot of different hydrocarbons. And it can also be used for carbohydrates. Those give energy to people and to animals. Now there's other major types of reactions that we'll study. Acid-base reactions transfer protons between elements or compounds. We'll spend 2 to 3 weeks studying acid-base reactions. Oxidation reactions transfer electrons between elements and compounds. And precipitation reactions combine soluble reactants to form an insoluble product that will sink. And we'll see an example of that when we work with double replacement reactions. Okay, so that wraps up this unit on reactions. Really, chemistry is about studying reactions all the way through. We're not going to ever stop studying reactions, but this deals with some of the major concepts that surround the subject of reactions, and we'll move on to our next lesson.